again, and you're welcome to physics class. I feel like treating waves today, definitely, and waves is a very versatile. All right, so for waves, we can define it because it's a phenomenon. When you talk about something called a phenomenon, it's an occurrence that you can observe as a result of situation of things, some factors being responsible. All right, so we can define wave as the phenomenon observed when energy is being transferred from one part of a medium to another part of the medium, and is transferring, energy is being transferred. We say that wave is transferring of energy from one part of a medium to another part of medium without the medium itself being transferred or being dislodged. All right, the medium remains, but energy passes through the medium in a way. So we say wave is a disturbance which travels through a medium and transfers energy from from one point to another without permanently displacing the medium itself. Okay, maybe I should come back with that. You have your physics textbook, you have different ones that you can consult for different definition of waves. But the basic things that we need to note there is that wave is like a transporter. All right, wave is a transporter. What is wave transporting? Energy. Energy is being transported from one part of that medium to another part of the medium. All right, and then in the process of that transportation, the medium is disturbed, but it is not permanently displaced. All right, so those are the things you need to know. When you drop a stone into a pool of water, you will see that the water is disturbed. The stone itself, as it travels through the water, has never and we never carry some particles of water from the top of the pond to the bottom. All right, the water will just feel depressed and come back up and then stay there. The water will not go to the bottom with the stone. All right, and if you see the stone going through the water, the stone is not the energy. The energy that the stone is transferring in the water is not even going in the direction in which the stone is actually going. All right, stone is just a particle that is, when you talk about energy conversion, so the mass of the stone, because mass is equal to energy. When you get to energy quantization, you get to some things. When you get to advanced physics, or what you call modern physics, you learn that mass can equal to energy, because E is equal to mc square, or the times Z square, as the case. So energy is mass, mass is energy. So the essence why we are using stone is to show that the energy that is equal to the mass of the stone multiplied by the speed of light can also be generated, in a way. So we need to know all of that. I don't want to go into those complications now. So let's talk about the wave. Wave is a form of, energy that is being transferred from one point to another in the medium, and in the process disturbs the medium, but it will never cause any permanent displacement of the medium. There are different types of waves based on two major categorization. There are different types of waves based on two major categorization. Let us just have some things to note here. Waves. No. Okay, waves. All right. Yeah. There are two major categorization. Now, you can categorize wave based on the medium of transfer of energy, and you can categorize wave based on the direction of transfer of energy. I said waves we have different types based on the major categorization. The first categorization is medium of transfer of energy. The second one is direction of transfer of energy. So when we have waves based on medium, there are some waves, they need a medium for transfer. There are some waves, they don't need a medium for transfer. Okay. When this is direction I wanted to write to, don't mind my phone. Okay, direction. Maybe I should just write it in a, let me do it this way. Okay, I have a better means of representing it. Let me do it this way. Waves. Waves. So I can have one here, medium of transfer. Then I have here direction. There will not be any, yeah. So we can have waves based on medium of transfer of energy, or whether they require a material medium for their transfer or not. Then we can have wave based on the direction. Okay, so if a wave require a material medium for its transfer, it is called mechanical waves. These things, you need to understand them. These are waves. Let me still do something. Let me use another slide. Let me do something. So this is wave. If I'm not talking, you will not be able to understand this. So I have to talk to understand this table. I have to talk. So here I'm going to do this. Though in a way, this is not exhaustive in a way. So I'm going to talk about medium here, no medium, NM, M for medium, N for no medium. Here I'm going to talk about direction. Let me use direction. Direction can be perpendicular, P for perpendicular, all right, L for linear, or LS, or linear or same direction, anyhow, or parallel, anyone you want to see. L for linear, or let me call it linear or parallel or same direction, LPS, linear, parallel, or same direction. So if a wave requires a material medium for, anyway, all these ones, okay, let me just go to the previous slide. Let me discuss this at length before I move on to that table. So if a wave requires material medium for its propagation, you say it is a mechanical wave. Note that, mechanical, that is, something needs to transport it from one part to another. But if a wave does not require a material medium for its transfer, we call it electromagnetic wave. A wave that requires a material medium for its transfer is called mechanical waves. A wave that does not require a material medium for its transfer is called electromagnetic waves. Note that. Let's go to the other one in terms of direction. There are some waves, as they travel, wave travels, but the energy that it transfers, or the medium in which the energy is transferred, also travel in different direction. If the direction of travel of wave is quite different from the direction of travel of the medium, we call it what? Let me see. Is there anyone can remember that? Transverse wave. That's what we call it. Transverse wave. Maybe now that you remember transverse, let me see if you can remember the other one. If the material medium and the wave are traveling in the same direction, not necessarily same like that, but they are traveling in a parallel direction, what do you call that? You call it longitudinal wave. Longitudinal. So for direction, we have transverse, 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 and then we have longitudinal. Longitudinal. Longitudinal wave. Yeah. Transverse wave and longitudinal wave. This one travels at right angle. That is, the wave is traveling this way, the particle of the medium is traveling this way. So they are at right angle to each other. That's what we call transverse wave. But for longitudinal, the wave is traveling this way. The particle of the medium is also traveling either this way or in opposite direction. But you can see that it will always form a parallel line. That's why I'm not going to be using the word same direction. It can be same, it can be different, but they were traveling at parallel line to each other or linearly. Both are traveling linearly. All this one, you will not get the details if you don't have someone explaining it in details like this. Some will just explain part of it like it's traveling parallel. Some will say it's traveling in the same direction, but it may not be the same direction. There are some waves that they don't travel in the same direction according to the transfer of energy. Some travel in opposite direction, but what we are interested in is the direction of travel will be linear or parallel to each other. So note that. Now, so let's go back to the one we call mechanical waves, mechanical, CL, and then electromagnetic, electromagnetic, magnet, from the word magnet, magnetic waves. All right. What are the examples? Is what I have prepared the slide on the next page. So when the wave require a material medium to travel, an example is water waves. For water waves, okay, sorry, I need to change this to, okay, yeah, direction of travel, parallel, I use transverse. It's at right angle to each other. So let me use T here, not P now. Okay, transverse with linear or parallel or same direction is the second one. All right, good. So when you have water waves, I've described water wave the other time. Water waves is like we drop a stone in water. What you are going to observe, I'm going to show you in a clean picture. So the stone landed in the pool of water like this, and then you see the bubble of water like a circle forming like this. You throw stone at the center, but water is being disturbed all around like this. What's happening? There is an energy from the stone that is dropped that is affecting the water in this format. That's what you know. So the energy is traveling this way, in this direction. But you see that the water movement are moving up and down, up and down. So this is the direction of movement. This is the direction of the vibration of the medium. So, but you will not notice this if there is no water. Water is the material medium. So water waves fills into this part. Water waves require a material medium, and then it's also a transverse wave because we can see that the travel of the wave and the travel of the medium are at right angle to each other. We can readily see that. So water wave is a mechanical wave. Water wave is also a transverse wave. So we can categorize it under those two. Some will say there are 4 types of waves. No, there are no 4 types. There are no 4 types. It depends on the category you are talking about. It depends on the criteria you are setting. If you are setting in terms of material medium that is necessary or not necessary, you talk about mechanical waves or transverse wave. Electromagnetic wave, sorry. You talk about mechanical wave or electromagnetic wave. If you are talking in terms of direction that it moves through, then you talk about transverse wave or longitudinal waves. Okay. What about sound? The way I am talking now, I'm talking into the air. Okay. Here is a steel particle. They just stay. Here is a mixture of gases, but they are just stationary in a way. But you will not only know that here is all around you, you will not feel it until it starts moving. When hair starts moving, then you say it's a wind. Wind is blowing. A moving air is called a wind. All right? That's why you have fan. The question you should ask yourself is, what is fan blowing to you? It's the same air in your room. The fan is just making the air to pass by in your direction. So all the air, want that stationary air to start moving. And when the air start moving, because of the way fan is configured, it will be pushing it towards your end. So when the air is moving towards your end, the ones that are not there will come to fill the vacuum, because life is not a vacuum. Our everywhere is filled with particular atom or molecule. So there are molecules of air all around us. When you begin to push it in one direction through the use of mechanical advantage you have in fan, then they say you have a wind. Wind is blowing. Yeah, that is it. Now, so the air is also a material medium. And as I'm talking, this is what happened. So the air is stationary at equal interval to each other. They are just like this. Now, anytime I talk, this pattern will change. And what you will notice is this. I want to demonstrate. You notice some pattern of compression and rarefaction. At some point, there will be compression, that is closeness of the air molecules. Because of what I'm saying, my words is blowing air. So it will compress some part of the air, it will space out some other part of the air. So this is what we call compression and rarefaction. So and this is it, I'm talking like this. So my voice is going in this way, then the air particle is compressing and in a form of a compression and elasticity. It's compressing and relaxing, like you are pressing a foam or a mattress. If you press it down, it will go down, it come up, go down. That's the way air behaves when you speak into the air. That's the way it behaves. So we call it compression and rarefaction. And it is the same direction that you will notice. It will move this way, move forward and backward in the same direction as the direction of the wave. So this one is called linear or longitudinal. So this is sound wave, SW, sound wave. It also requires a material medium, but the direction of travel compared to the direction of the medium is the same or is parallel. So you can see this category now. So in this category, we have water waves, we have sound wave here. Water wave require a material medium, sound wave also require a material medium. The direction of travel of water wave and the direction of travel of the medium are at right angle to each other. They are perpendicular. Yes, that's the word I'm looking for. They are perpendicular to each other. That's why we call it transverse mechanical waves. It is transverse and it is mechanical. The other one, sound wave, is mechanical because it requires air. If there is no air, you cannot talk and someone will hear you. That is why they say in a vacuum, it is always silent. We have tested it. If you put an electric bell in a vacuum and you ring it several times, nobody will hear. Even though you are close to it, you won't hear anything. Sound requires a material medium. That's the proof of that practical. And this is one of the things I enjoy. When I was in secondary school, I had access to practical physics lab. A lot of things that I practicalized. Though then there was no YouTube where you can go and watch all these practicals. You can go on YouTube and just type vacuum experiments or sound in a vacuum experiment. Just type it on YouTube. It will bring different ones you will see where people have actually demonstrated all these things. Don't just watch movies and all of these skits on YouTube. Watch intellectual, educational things that will improve your learning, so that when you are talking, people know you have stuff upstairs. So one of the things I enjoy doing is I enjoy staying in the physics lab a lot. I enjoy watching my teacher set up experiments and all of that. It really makes me to be fascinated in the world of physics. Unfortunately, I am not the electrical engineer I wanted to be, but it's fine. At least I know those things. So here, like I was saying, sound wave causes this, and so it is called longitudinal mechanical wave. I've spoken so much on this. When you beat drum or you play keyboard or trumpet, anything sound, it's under mechanical wave and it will give you longitudinal wave, all right? And I'm going to still be demonstrating some things later. Let's talk about what if material medium is not needed? What type of wave can we think about? What if material medium is not needed? What type of wave can we think about? Can anybody help out? If material medium is not needed, as the wave travels, you don't need a material medium for its travel or for its propagation. An electromagnetic wave. In fact, from the word electromagnetic, light wave is an electromagnetic wave. Light does not require any material medium. It just go. There's no material medium necessary to transfer that waves of light. It doesn't require any material medium. All right. That is why sun rays can go through the cloud. It does not, it just come. It just come. All right. And when I say electromagnetic, there are some laser beams, there are some electromagnetic rays. They don't require, when you talk about gamma rays, they just pass through anything. They don't require you to, nothing can disturb them. They will just go. All right. Like I said, if there is no hair around me and I'm talking, nobody will hear me. That means I need a material medium. But for light rays, you don't need a material medium. They just go. They just go. So light rays can go, and light rays are transverse waves. Because they don't need, when they go at right angle to the transmission, any medium, they just go. You don't require any material medium. It is when a material requires a material medium that you can now check which direction is it going, which direction is it moving, and all of that. Now, you might be asking, okay, so when you say when wave pass and they transfer energy, so which energy is light transferring? Light is transferring the heat energy. Sun. You are not close to the sun, and sun is coming on Earth. Heat energy is following. You walk in the sun, you get hot. It transfers energy from one point to another. That's a perfect definition of waves. So since no material medium is needed, of course, you cannot now say transverse or longitudinal or anything. It may not apply in a real sense of it. But actually, we have been able to find out, because there is another topic called wave particle duality of matter. Matter can exist as wave and at the same time can exist as matter. So we found out that light also is transverse in nature when it is converted to matter. All right. Well, that is not for this topic now. Let us now move away. We want to check some things under this. We are going to liken this to some things we need to know. Let's move to the next slide. I want to demonstrate some things to you. Okay, look at this. So I'm saying that we can graph both longitudinal and transverse wave can be graphed. We can graph it using a sine wave, what we call sine wave. We can graph both longitudinal, sorry, I'll bring it back up. Can graph it this way. Okay, I think I just need something like this. The process, and I'm going to demonstrate it. Look at this. Like I said, the particle of water, when you drop a stone, you just observe upward and downward movement of water in a pool. And then for the particles of air, you will observe a point of compression. This is where the sound is loudest. And a place of rarefaction, spacing out. This is where the sound is lowest. And then you also, this is how it behaves. And then it spraces out, it compresses again, then it spaces out. So it's like playing accordion, So the wave is traveling in this way. Particle of the medium is traveling in this way. The wave is traveling in this way. The medium is also traveling in this way. So both of these A and B, because on both we have seen a space where